All right, so let's talk a little bit about cell voltage and it relates to equilibrium. What if I have an electrochemical reaction? Can I estimate the equilibrium constant? Turns out you can. At equilibrium, delta G is equal to 0, and therefore E is equal to 0, and our Q becomes a K because we're at equilibrium. And so if we use our Nernst equation, E is equal to E standard minus 0.0592 divided by N log of Q. Substitute E equals 0, Q equal K, then 0 equals E standard minus 0.0592 over N log of K. You start solving for K, you get log of K being equal to N E standard over 0.0592. And then so K is equal to 10 raised to the N E standard over 0.0592. This will allow us to estimate K, but it's probably not going to give you an extremely precise result. But notice if the E is negative, then K is going to be small, meaning it's very reactant favored, not likely to proceed. Where if E is positive, you're likely to get a large positive. Depending on your calculator, if the voltage is extremely large, you may get something that kind of blows your calculator up, depending on which kind you have. So you might have to express it more of a scientific notation or simplify it more by hand if you have a calculator issue like that. So let's look at an example. Let's look at our copper silver redox again. And we calculated this cell potential before, so we'll just reuse it for the sake of not prolonging the video. So we're going to use that. Remember, N was 2 for this particular reaction because we have the copper redox being 2, silver redox being 1, so we multiplied by 2 to get the 2 electrons. Past that, we'll use what we've already done. And you can see there's where we calculated the standard reduction potential, which was 0.46 volts before. If you're unsure as how to do that, go back and review my introductory video where I walked you through calculating these reduction potentials. We're just going to use it in this case. So K is equal to 10, and this can be raised to all of this. And just for the sake of not having to write tiny, I'm going to do it with a little caret here to indicate all this in the parentheses is in the exponent. So it'll be 2 times 0.46 volts divided by 0.0592 volts. And then we're going to run that through our calculator. 2 times 0.46 divided by 0.0592. You're going to get 10 raised to the 15.5 power. We'll go ahead and crunch that out, but you kind of want to at least have that in case your calculator blows up and won't handle the load. In this case, the calculator will handle it, but if it gets really big, it may blow your calculator up, and we'll call that 3.5 times 10 to the 15th power. So a very product favored process, as we imagine, because we don't tend to write that as an equilibrium, rather one directional arrow. And in those cases, the equilibrium constants, if you calculate them, would be extremely large. But this would be your answer.